I have a new look, I'm just going to have to show you. This behemoth is a Xerox MemoryWriter 6040 from about 1987. It was a donation. Thanks. I think. It's a word processor, one of those machines that bridged the gap between the old typing pool typewriter days and the modern microcomputer days. The thing is built around a daisy wheel electric typewriter, but it's also got a floppy disk drive and a monitor and a computer inside that can run word processing software. The thing is built around a daisy wheel printhead. This is the daisy wheel. It's an embossed disc with all the various letters the thing can print on it. The way it actually makes letters is it rotates the daisy wheel until the letter it wants is under the head, and then fires a solenoid which stamps that letter onto the paper through a ribbon, which I've removed here to get access to the printhead. It does actually function. If I turn it on, it resets the printhead and rotates the daisy wheel so it knows what element is under the solenoid. And then I can press keys on the keyboard and it types stuff. Being impact printers, you end up with the shape of the letter more or less embossed into the paper through the carbon ribbon, which produces incredibly crisp results. This machine also has a bit of a party trick, which is the ability to remove letters from the paper after printing. As you can see, it doesn't work brilliantly, but that's mostly because the rather elderly special ribbon that it uses for this is rather elderly. But of course, this thing is more than just a typewriter, it's also a word processor. There's a small computer in the back which uses this cute little 9-inch CRT on a swivel arm for ease of access, and the floppy drive, which is here, to allow you to write documents offline and then print them out later. Back in the old typing pool days, this was an amazing feature. If you were a secretary issued with one of these things, it made you far more productive than using a traditional dumb typewriter. You could write documents with fewer mistakes, faster, and you could make multiple copies of a document really easily. Because remember, back in those days, photocopiers weren't really a thing. If you wanted multiple copies of a document, then you, as the secretary, you had to type multiple copies of the document. This is a late model word processor. It has the ability to store documents on a floppy disk. Some of the earlier electronic typewriters couldn't do that. They could store text in memory, but this thing is significantly more sophisticated. In fact, it will even load word processor software off the floppy disk, which is a bit of a pain because I don't actually have that floppy disk, so I don't have the word processor software. Without it, the thing operates as a rather simple and not very featureful dumb typewriter. Things are not helped by the international keyboard. International means they try not to put words on because that means they have to translate it into different languages. So instead you've got all these meaningless symbols which I don't know what they do. Some of the ones over here I've managed to identify as setting tab stops and they actually function, but most of these just don't do anything. The double beep means something went wrong and you get the error message on the screen. The keyboard is excellent with these big chunky keycaps with smooth surfaces. The key feel is deeply weird. The keys are super tactile, but also very smooth and not clicky at all. I think it's a rubber dome inside, but it's not like one I've used before. It's actually very nice. The keys sort of pop down once they pass the critical point. The keycaps themselves are these super chonky things with sides about 2 millimeters thick. They're triple shot using brown, green and white plastic to produce the legends on this side. They're very high quality. The mechanism itself is, I think, some kind of slider over dome. I don't recognize it. I'll know more once I take the keyboard apart, because of course I'm going to take the keyboard apart. Sadly, the keyboard is not completely functional. Most of the keys work. However, some of them are dubious, including the spacebar, which is a bit of a shame because you kind of need the spacebar to work, which is why I haven't really done a typing demo on this. Both the screen and the floppy drive seem to be add-on units that didn't come with the base typewriter. You can see the screen is attached by this unit here and plugs in via this cable, which carries both data and power. The floppy disk drive can also be easily removed, and it just folds down like this, and then you can undo this extremely stiff and difficult to remove connector, and this unit just comes off. Once that's done, taking the lid off is quite straightforward. First thing you need to do is move this back and flip this up, and then press these two catches, which then lets you lift off the entire print roller. Optionally dropping parts on the floor. And once that's done, you just need to undo these 4 screws here. Then the top shell just, or at least should just, lift off. And that reveals the works. I'm going to remove the keyboard later, but first let's focus on the computer part of it. The main board is underneath this shield, which should just pull off. It was once fastened on with this extremely crusty tape, revealing the main board. It does also reveal the linear power supply that makes the whole thing go, which is enormous and contains some enormous and very angry capacitors, so I'm not going to touch it. But this is the main board. This is the bit that interests me the most. Let's remove this and take a look at it on the workbench. This cable goes to the print head. This one, it goes to the stepper motor that drives the print roller. These go to another stepper motor. There seem to be 2. Oh right, one will be for the print roller and the other will move the head backwards and forwards. There are a couple of plastic clips here. That one's disconnected. There we go. And it just pulls off. Although now I've removed the system board, I do see something quite strange. This is the connector for the floppy drive. It doesn't connect to the system board. I can see the cable running underneath the power supply board here, but I don't know where it goes. And likewise, this is the video connector, which plugs onto the power supply board. It doesn't connect to the system board. In fact, the system board only has one connection to the power supply board, which is this one. It's for the power supply. So this is going to need some more investigation. But let's take a look at the system board first. In fact, it's all a bit puzzling. This is the CPU. It's a 8031. It's a version of the ubiquitous 8051 8-bit CPU that's been in use since the year dot and still is. This is the EEPROM containing the software, and all the rest of it that I've been able to identify is like simple 7.4 LS logic. These 2 chips, I don't know what they are. These two chips, I don't know what they are, and this chip, I don't know what it is. I thought that maybe this was RAM for the CPU, but I don't think it is. The pinout and size is all wrong. These two are too far away for RAM. This board seems to be unable to run the word processing software. So now I'm wondering, is this in fact just the board that controls the printer and that the actual applications processor is elsewhere? That would explain why there's so little on it. I think I have to go back to the machine and do some more investigation. Looking at this big connector on the motherboard, I thought this was the keyboard, but I now don't think it is. There's some labels down here. I see NPOR and VSync and HSync. VSync and HSync are for the video, and NPOR is here on the power supply. So I think that this connects the system board to the applications board. And the applications board communicates with what I thought was the system board via that NPOR line. In fact, over here I can see PNorm and NPOR, and I wonder if these are input and output, although I do see an SDAT, which seems to be a much better candidate. Let's take the keyboard off and see what's underneath it. Ah, that's not the keyboard, that's just the extra keys for the keyboard. Working around the camera is super awkward. Okay. Wow, that's heavy. Ooh. There's actually a lot of stuff in the way, so I'm wondering if this slot needs to come out first. It's not actually fastened down. There's a wire up here for the stepper motor. So now I should be able to lift these, revealing, ooh, a big thing. This is definitely a computer. These two ribbon cables. This one is for the floppy disk controller. This one goes to the what I thought was the system board. That connects the keyboard. Oh, and this is the keyboard extension. Okay, let's take a closer look at this. So what do we have here? Well, the answer is quite a lot. This is 256K of RAM. This is another 8K of RAM, which looks like it should be video memory, except over here there is yet another 4K of RAM. So there's an 8051 CPU here that is probably not the application processor. The 8051 has a built-in ROM with some software on it, so this will have been pre-programmed, so I suspect this is operating some peripherals. These two big chips are gate arrays, sadly, because gate arrays can do anything and they're undocumented and who knows what they do. This is the floppy drive controller, which is standard, which is nice. These are EEPROMs. Well, these are EEPROMs. This is probably a ROM. This is a mask ROM. But I don't know what it's connected to. And this, the only socketed thing on the board, is probably the application processor. And I haven't opened this yet. So let's do so and see what is in there. If I can figure out how to do it safely. Like that. I may not get it closed again. It's a 80188. I had to go look that up. Turns out that the 80188 is a variation of Intel's 8086. It's got some more extra instructions and some built-in peripherals and so on. It's intended for the embedded market, which this is. So I'm a little disappointed. I was hoping it would be a bit more exotic than that. Oh well. Let's see if I can get the lid back on, shall I? So this pushes down and then this clip then goes over the top. Somehow. There we go. And it might even work afterwards. When I first took the lid off and saw the 8031 on the board at the back, I did get quite excited because I thought this might be that very rare thing, an 8031 based microcomputer with, keyboard and floppy drive and CRT controller and so on. The 8051 is a bizarre architecture, and some of these word processors did revolve around them. And I've been looking for one that was programmable as a microcomputer as opposed to an embedded device like this chip here for quite some time. But this is not it. Even more disappointingly, the ROMs are all soldered down, not socketed. So getting them off to dump them will be a pain. Well, regardless of what I want to do with it, there is one piece of work that needs doing immediately, which is to remove this lithium battery, because these always leak eventually and always cause very bad things to happen to the PCB, including major amounts of damage. Nothing kills old computers more than leaky lithium batteries. So let's use brute force to pop the spot welds. Yeah, okay, let's just use metal fatigue to avoid damaging it. Yeah, those marks were me. There's a track there. I hope I haven't damaged that. It's a 3 volt CR14250. Huh. It actually looks reasonably intact. Okay. Well, I'm taking it off anyway. I mean, I have taken it off. It's not like I'm going to put it back again. Let's just check that track. Looks like it connects to one of these. Yep. Okay, I did not damage that track. Down here is a 16 megahertz clock crystal. Here is an 18.432 megahertz clock crystal. And here is a 12 megahertz clock crystal. I bet this one runs the 8051. This one runs the 80188. And this one provides the clock signal for the CRTC, which is this. This is the thing that generates the video signal, which gets dumped down one of these pins. All right, let's take a look at this keyboard. So, and this shows us the back of the board, which is empty. Here is the back of the keyboard proper, which is, as is tradition for keyboards, big and cheap. We've got, what's this? Huh. That's weird. That's very weird. What is that for? I don't know. Got a lot of 7.4 LS logic for doing the keyboard decoding, plus what looks like a custom gate array thingamajig here. No, it's not. It's an 8051. Yet another 8051. That's the third one that I've seen on this system so far. Undo the screws. So what is now holding the board down? I think it's these things. So I think they might just pull off. No, that just wants to break. they screw off. Oh dear. And that reveals a rubber dome keyboard. That were a very intriguing rubber dome keyboard. These are weird. Are they supposed to just pop down like that? And oh, I know why those keys aren't working. It's not a rubber dome, or at least it is a rubber dome. Oh dear. These silver foil pieces push down onto the PCB. And the reason why the spacebar wasn't working is because the... yeah, this is foam over foil. The foam's disintegrating. Oh dear. And you see me manipulating it is causing these things to just pop off. Right, this is dead. They can be repaired. You need to stick on new bits of foil, but I've never done it and don't really want to. These are capacitance keyboards. They don't work by making a electrical contact. The piece of foil comes down over these pads, and then the microcontroller can detect the change in capacitance and therefore figure out which key is being pressed. That's disappointing. Every single one needs to be replaced. On top of the rubber domes, this piece contains all the sliders that push down on the rubber domes, which is super heavy and super high build quality. This is actually rather nice. I don't know if they're sprung. Well, the spacebar's sprung. The other keys are not. Yeah, these are just falling off everywhere. Okay, let's just attempt to put this thing back together. Yeah, this is not going to work again when I reassemble the thing. It's just in too bad a state. But let's not lose any of the pieces, because that would be stupid and embarrassing. Before attempting to desolder those ROMs, let's take a look at this thing. This has got the extra buttons on it. There's nothing of any great interest on it, apart from this thing, which is a hard piece of plastic that I haven't figured out what it does yet. And if you look down here, there is actually a component there. So let's take the lid off and see what we can see. There are a lot of screws here. Okay, this just lifts out to reveal. Well, these are the buttons. As I thought, they're just buttons, but this thing is a slider. There's a thing here as well. So the little slider is completely hidden underneath this plastic thing. Like that. Maybe you're supposed to take this off and plug a slider knob on it. Maybe it's a feature that isn't supported on this model. Even so, very strange. Okay, let's have a look at desoldering these ROMs. This is all a bit experimental. So I'm going to just reflow some of these joints with some fresh solder. Then I use this extremely safe AliExpress plunger desolderer. Let's see what happens. And that has sucked the extra solder I put on off, but hasn't actually Removed the existing solder. Okay, that is not going to work. This looks so easy when other people are doing it. Well, that is one red hot and probably broken chip. And the board hasn't survived very well. There's a slightly mangled cap there. Oh well, it's probably broken now. Let's try the other one. Seriously, this is much harder than the YouTube videos say it is. Well, that was a horrible experience, both for me and the chips. They were actually physically hooked around the PCB. I didn't notice, so I ended up using way more heat than I should have before I realized I was supposed to use actual brute force. Anyway, I've plugged one into the chip reader, so let's see what it does. It seems to think it's a TMS 2764, according to the label on the front. So let's try TMS 2764 at dip 28, fetch the chip ID. Okay, doesn't have a chip ID. Try and read it. Well, it read something. Let's see if it actually makes sense. There's not a lot there. Let's try the other one. The one it's currently in is the one where the sticker ends up with 60. This is the one where it ends in 70. See, I would expect them to be bigger than 8K, is that? Definitely says TMS 2764-25JL. I wonder if this is actually just some kind of bootloader and the real data is on the mask ROM. That would be interesting. Also, the way this one shows FFs, I think means it's dead, and I've wrecked it. Let's just try reading that one again. Okay, there's more here now. So it was clearly a dodgy read. So we've got two ROMs that look kind of similar. They're probably interleaved so that all the high bytes will be on one and all the low bytes will be on the other. This is very common with 16 or 32-bit systems. But now I think of it, the processor here is an 80188. The last 8 means it's got an external 8-bit data bus, so it reads a byte at a time. So I am not sure. Let me do a bit of research just to see if I've got the ROM size correct. Yes, I was right. It is a 8K device. The one I have here is the TMS 276425. So yeah, that actually seems to be fine. So I've written this little program which will uninterleave the binaries. So I run it. Okay. And I should now have a out.bin, which looks deeply suspicious because every byte is doubled, suggesting that both ROMs contain the same data. Or at least, both ROM images contain the same data, suggesting that I have read them wrong. Fantastic. Okay, the one currently in the reader is 70. Oh, right, I think I've read them wrong. 70. Swap ROMs. Read 60. Okay, I think 60 was the bad one. Yes, it is. and it's still producing FFs, which means I think it's terminally bad. So that looks more plausible. Although the data looks kind of weird. I would expect to see more coherent pairs if this was interleaved. So maybe it's not interleaved. Maybe it's just one after the other. In which case, assuming that the one with data in it is the first, if I do this, then, but it doesn't look like machine code. Here it is loaded into Ghidra, and it's failed to analyze anything, but if we put the cursor here and press D to disassemble, that looks like garbage. That data looks kind of interesting. So these seem to be, are these groups of 8? I think they are. I know what this is. These are the character set ROMs. So here we are with the thing loaded into GIMP. Let's change this to black and white 1-bit. Yes, that's graphics data. And now we change the width to 8. And there, if I adjust the offset, that's our font. So if I open that and then zoom in, we can quite clearly see characters. Interesting looking font, to be honest. It's quite bold. That is intriguingly chunky, and there are all the weird characters, some of which I saw in the error messages. Right, okay. You know what this means? I have to desolder the other ROM because that's the one that's got the application in it. Great. Well, that was slightly less awful than the other two, but still quite awful. I have to invest in a proper desoldering gun. The ROM claims to be a TMS 27PC256NL. So read that device into... Oh, I also got the ROM numbering wrong. The heat gun managed to do a job on the labels, which I think are plastic. And the last few digits have disappeared on each one. Okay, that's much bigger. So the 60 ROM is in fact 80, and the one I've just read is 60. So what's in this? That looks like stuff. Not very big, 16K. I suppose if this contains the basic typewriter software and the bootloader, that's a lookup table. Graphics data. Okay, here we have garbage. That looks weird, but not obviously graphical. I think this is our lookup table. 40 would look quite similar to that. Nah, no graphics. Let's stick that into Ghidra and see what comes out. And here is some stuff. Let's try disassembling it. That looks like stuff. So we can immediately see, this is loading one of the segment registers. That's clearly where the RAM is, or at least some of the RAM. This is doing some initialization of a local workspace, looking for a long jump instruction, because that will tell me the absolute address of this code. I just loaded it at 0 because I didn't know where else to put it. But these are all relative jumps, so don't contain the actual segment address. That's loading a segment address of 0 into DSES and SS, which suggests this is in fact loaded at the wrong place. because putting the stack in ROM is not going to do any good. But yeah, we can see that this is actually x86 machine code, which Ghidra is making a reasonable job of disassembling. It will, of course, all be garbage until I manage to find what address it's loaded at. Yeah, this is code, but Ghidra has seen memory references to it, and so is getting confused. I can actually, if you go to Window Memory Map, I should be able to change, here we go, change the start address to there, clear everything. Let's do the disassembly again, and it should do a rather better job of it. 2000 hex is going to be the wrong address, but it's less wrong than 0. Yeah, this is a much cleaner disassembly. And over here we have the decompiled code. Oh, this hasn't worked. Oh no, that is an explicit reference to the code segment, which means this really is a variable in code. Now, the trouble is that this is clearly a lookup table. The trouble is that without any strings, and I don't think there are any, actually deciphering what this does is going to be hard. We kind of need to find some code that we can guess what the purpose actually is and work up from there. Here are finally some long call instructions, call far, which have the segment baked into them. So this makes me suspect that all this code should be loaded at F000, but these offsets are all quite high. B260. This code doesn't go that far. This is only 32K. So maybe this is calling some other code. But where would that code be? Well, the obvious answer is loaded from floppy disk. So are these funcs to entry points from code loaded from floppy? There's quite a lot of them. Ooh, do you know what this is? This is a string. Excellent. So this is clearly, in fact, all of this is probably stuff to load into a message, display to the user, to prompt the user to, well, you know, insert a disk. So all I need to do is to find a reference to this address, which I should be able to do. 4426. I'm looking for 2644. No. 2644 here. Not sure why it didn't show up usefully there. Oh, because it hasn't been disassembled. So we go up here to something that looks like an opcode, disassemble from there, and here we go. Move 4426 into SI. We know this is an address. So we know that this is a char, and in fact it's an array of char. I bet 1e is the length. So tell it it's an array of 1e. Yes. You see how neatly that has fit. And then here there's another message, which I bet is also here, and is also 1e long. So this is type char, it is 1e long. Though I bet that 03 is a weird character that we can probably look up. And is this machine code? That's machine code. All right, we have a place where we can start looking. So what's going to happen here is it's going to draw this onto the screen somehow. And LOD SB here does a memory copy. So over here in the decompiled C, we can see that, as it were, ivar2 contains 1e and is being decremented as part of the loop. So that's clearly the counter. I need to actually turn this into a formal function like so. This turns white, indicating it now knows it's a function. Now I should be able to rename one of these, rename variable. Count. Okay, count equals count plus -1. Well, count is not equal to 0. So we are here, puvar1. Yeah, this is decompiling lod.sb in a slightly weird way. puvar2 is our source. And it is a retype variable. It is a char star. And that makes a lot of the rest of it happier. pcvar1 is temporary, so we can rename that to p. No, it's not. That's the wrong one. pcvar1 is temporary. This one is dest. pcvar1 is our temporary. That didn't work. P. Duplicate name. It thinks P is in use elsewhere. Anyway, that doesn't matter too much. That's a temporary. So dest is probably where our screen memory is. And this is here. Destination pointer. What segment is that writing to? I have forgotten how lod.sb works, to be honest. Anyway, this tells us probably where our screen memory is, although it could be some kind of buffer that's then written to the screen later. But down here it calls a function. Let's actually rename the function we're at now to insert disk prompt. So this function sets a bunch of variables and calls this, which jumps elsewhere. Interesting. I wonder if there's a bit I'm missing. Anyway, where is our insert disk prompt being called from? Ghidra hasn't seen any yet, but we know this is at address 43D4, so search memory for 43D4, and it's done the little endian conversion for us. Search all. Not that one, but I bet this one is it. Yep. 43D4, disassemble there. Ah, 43D4. Right, I think I know where our ROM lives. I think it lives in the top 8K of that segment. So move it to F008. That is the top of memory. So 4000 here is probably RAM. Rename that to ROM. Let's add a new memory block at 4000 called RAM. And this is 256K 262144. This might not be the 256K. It may be a different memory block, because remember there was that extra 8K or so in the middle of nowhere. So that could be this. That 8K could be for system use, and the 256K of RAM lives elsewhere. Anyway, let's go back to our insert disk prompt. And this is called from, we now know, two places. There, function, it doesn't seem to be called from anywhere. And here, okay, functionify, also not called from anywhere, but E63C. Nothing. Okay. This function here that insert disk prompt is calling is very clearly setting up a table of some kind. Now this is probably, well, this is probably part of the floppy disk code. It's just done something with a insert disk 0 label. So is this a floppy disk command? that it's setting up? The answer is no, it's not. This is the data sheet for the 1772 floppy disk controller. I was thinking of the 765 floppy disk controller, where you pass it a command block and it does stuff. But the 1772 works differently. Instead, you program several different registers and it does a thing. So this is setting up some other block, which I don't know what it does. It then calls this, which calls this, which calls this, which calls this, which does this, which does a thing. Okay, I was hoping to find something that was clearly reading from the keyboard, because that would tell me where the keyboard ports are. But that does not seem to be especially obvious. This is an array of words. You can see that the low value keeps increasing until suddenly the 0 here rolls over to a 1. So tell it it's an array of words, and here are the values, which look quite sensible. I bet this is a jump table, that these are offset into a thing. So FO3C, probably used by this stuff up here, load 3C into BX and dereference it. Right. This code is executed at a different segment than the rest of it, so that this is actually FFOO002. This is due to the weird way in which x86 segmentation works. And I don't actually know how to persuade Ghidra that this is at a different address. But this then is jumping via the lookup table. So I think this is part of the reset code. And here, indeed, I just looked it up, is the reset vector. When the system starts, it jumps to this routine. This jumps to this routine, which initializes some ports. Then it jumps to this routine, which initializes the rest of the system. So turn that into a function, rename it, initialize. And then this does things. There's a fun thing you can see from the decompiled code looking at the startup routine. If anything goes wrong, it just hangs in a busy loop. I mean, what else is there to do? It's not like you can print an error message if the screen system doesn't come up. Here's another interestingly specific string, sdobj.com, with an 01 on the front. That suggests that it wants to look up in the file system a file with this name. Well, we're clearly not getting anywhere following this, so let's try something else. When the machine boots its word processor disk, it will eventually want to run the code it loads off the disk. So there should be a jump recall instruction which will look different from any of the others. So let's have a bit of a search around. We can see here there's an absolute jump instruction that takes a segment and offset. And Ghidra has rendered it as F000, FFOO, but if you look over here in the actual bytes, it's actually calling segment FFFO offset 0. So assuming that the word processor code gets loaded at the beginning of a segment, if we search for EA0000, we might find something. Hey, look, what's this? This is a jump instruction. It's jumping to... That's interesting. I didn't think there was memory there. So this is clearly jumping somewhere. So back off to about here and disassemble. That looks like odd code. There it's jumping to 3A2E colon 0700. I wonder... I'm unconvinced about this. I think that I'm looking at a data table. Yeah, I think that's garbage and I was wrong. Oh well. Luckily Ghidra has an undo feature. Alright. So we haven't found a long jump. How about a long call? Now, there were some somewhere. Here's one. So this is jumping, well, calling to segment FF00 address 0002, which again Ghidra has unhelpfully normalized. So if we look for 9A00, like that, what do we find? Nothing. All right, what have we got for other calls? If I can find an indirect call, that will also help. So search for instruction patterns. I don't think this is going to search for call instructions. I think it's going to search for call instructions that happen to use the E8 opcode, which is not what I want. Yeah, all that's done is search for E8. That's not helpful. Turns out x86 instruction encoding is really complicated. So this is a simple assembler. This tells me that call CX turns into FFD1, call BX turns into FFD3, and so on. FF is a general purpose prefix. It does a whole bunch of things. Part of the opcode appears to be in the D bit. The 66 here can be ignored. It's just a prefix in this assembler because it thinks it's assembling 32-bit code. So I'm going to have to search for multiple things. So FFD1, nothing. FFD3, nothing. I have just remembered that you can search the disassembled program text, which is very helpful. So these are the first 500 call instructions that it can see. Here are all the call Fs, and they are all segments that we know about. All the jump Fs. There are 3, and we know about them all. I found something. I found something interesting. There's this weird code here. What this does is it writes an EA into this location and then jumps to it. Now an EA is, of course, a far jump instruction. You can see it right there. So this is clearly doing some kind of indirect jump. So if I follow this, here is far jump opcode, but then there is far jump segment and far jump offset, which is where, well, the segment and the offset go. Interesting thing is that Ghidra has not found any references to these. But if we do a search for 604, so that's 0406. So 0406 is appearing in memory, but it's not the constant 0604, which is annoying. But we do know that this routine here is the thing that does it. So we can assume that this probably has something to do with making long distance calls. And we can see that it's called by nothing. Interesting. One thing I have identified is that the ROM appears to be divided into 2 parts. There is the main code, which is loaded at F8000000, and then there's this piece of code here, which, according to Ghidra, starts at F000 F000 here. But if you actually look at any far jumps that it's making, the code thinks it's loaded at FF000000 because of the unique nature of 8086 addressing. This is all deeply irritating. So this is probably some kind of microkernel or executive. So here's a place where it's calling one of those executive things. The segment here is FF00, but Ghidra's rendered it like this. It's put the second F over here. And the offset is 0002. So this is at F800, so that should be, yeah, FF00 0800. And there seem to be no direct references to it. So either this is unused, or it's been called by something I haven't figured out yet. I do see it's calling this routine, which is doing stuff around the 600 area. It's not actually touching the stuff. Oh, wait a minute, what's this? 606? this is actually the offset. Didn't I search for that? Maybe I just searched for the segment. Or maybe they're reusing the same thing somewhere else. No, this is called from our long distance call function, so this must be setting up the offset. What I don't see is it writing to this. This is reading from the value. It's also annoying that this is not showing the correct cross-reference. I can actually fix that by adding a manual reference, but I shouldn't need to do this manually. So here's the thing. At the top of the executive part of the ROM, there is this function which I've called argument. That shouldn't be called argument. That should be called executive entry point, because I think this is the entry point to the executive. You call it giving it the number of an operation and an argument, and then it goes via this jump table and does a thing. However, because of the segment problem and Ghidra, it's got most of these wrong. So I'm just editing all these references to point at the right place. And I am wondering if one of these will actually call our mysterious function. And the answer is no. Our function is at F800 and none of these go anywhere near that. So it's still a bit of a mystery. What is calling it? It's likely to be another of these references that Ghidra hasn't quite worked out is an address, even though it can clearly see their addresses. Another interesting thing is that a lot of this code is making actual system calls with the int instruction. And what this does is it jumps to an address in the jump table at the top of memory. The first kilobyte of memory on the 8086 is devoted to a big array of segments and addresses. So it's calling entry point to 0 a lot, which is being initialized from here to this. So our hex 20 interrupt handler is at F800 to F2. So that should be, can I do this? F800 to F2. I can. Oh, I seem to have found it and labeled it before. Oh well. So what is this actually doing? It is in turn indirecting through a table at 317 relative to the code segment, which is F800. So here is the jump table. So each of these is a word, and it's an array, and these are more offsets relative to F800, so I'll need to fix these up. But none of them go to our function, except that one. No, wait. The code segment is F800, and our function is a FF00 job. Okay, we're looking at the application code here, not the executive. And I think we want to be looking at the executive. But that is interesting because we saw the executive making int20 calls. So maybe that is how it calls the application, or maybe I'm just wrong. I think I've got it. This piece of code in our long distance calls stuff, it sets up some variables here, 1, 0, and 3. It then calls the executive in a loop. And here there is a reference to the number 9. 9 is the number of sectors on one side of a standard DD disk. I think this is our floppy disk loader code. I think that 601 here is the current sector. So it loads a sector, advances to the next one. If we hit sector 9, reset to sector 1, and presumably switch tracks. So if executive entry point 7 loads a sector, OX400, that's not a common sector size. Sectors on standard IBM disks are half a K long. That's OX200. If we assume that 602 is the current track, although I said that 9 was the number of sectors on a track, but we are starting at 3 and we are incrementing before the comparison, so the highest value that this would be allowed to go to is 8. So this increments it to 9. No, wait, hang on, I'm off by 1 because this is a less than. The sector number goes to 9. This does not fire. I wish there was a way to flip this if, so it continues on. Once it gets to 10, 9 is smaller than that, and it does this. Okay, so it resets the sector to 1. If the current track is 0, switch to track 1, and then do a thing. Otherwise, we're on track 1, then switch to track 0, increment. Oh, it's the side, not the track. That makes this one the track. Okay, if the current side is 0, switch to side 1. If the side is 1, switch back to side 0 and move on to the next track. Okay, this is the loader. And it's loading from an absolute position on the disk. So this is probably the main program loader. Now, after every track, it goes on to do this stuff. This value here is being read via SI. That has to be passed into the function. So let's just add this to pointer custom storage, because this one needs to be in a register in SI. Okay, so that should have simplified the code a bit. Now this is being passed in from long distance calls here. So here 15D, this is relative to the code. So let's add a reference memory. It is relative to FF00, that's our current code segment, which makes this garbage. So maybe our code segment is not FF00. Change this to F8. Is that more sensible? No. Okay, I don't know what that's pointing at then, but we know it's a pointer. Okay, what's this loop doing here? Well, I can see that the outer loop is using bvar4 and cvar4. bvar4 and cvar3. It's clearly a counter. It's counting down. So I think argument 2 here is number of sectors remaining, like so. And also we know that this is a byte, which should hopefully simplify some things. Right. Hang on. This isn't working right. No, Gidra doesn't like that. I don't know why. The reason I know it's a byte is because this nonsense here is put 7 in DL and it's using DH for something else. I may have the signature of this wrong. Let's actually just get rid of that. That might take 2 parameters. Can I change the type of it yet? No. I changed the type of the variable and then it creates a new variable to put the count in. Okay, let's leave it there. bvar4, where is that being created from? Initialized rather. Oh, cvar3. cvar3 is the number of sectors remaining. Yeah. This decompilation is getting thoroughly confused because it thinks that this thing is a word. And that's one reason why this is confused too. So what is actually this doing looking at the machine code? Oh, it's comparing what's just been read with a table in memory. Here's our comparison loop. CX is the count, that's part of the loop. So can I do something about that? I change this to a byte like it should be? No. Doesn't like retyping. So rename that as bytes left to compare. Right, this 400 here is our load buffer. So we know that this is an array of bytes that is 512 long. And hey, look, it fits perfectly before the next thing. Call that sector buffer. So it's comparing a signature. And if the count left reaches 0 and the signature matches, then it's loading the jump offset from here. This is not loading multiple sectors. It's searching for the boot sector. It loads one sector at a time. Is that now a char? Type variable to byte. Okay, it's stuck now. Rename to sectors left to search. Now it's sticking. Okay. This is also a byte. And I can just rename these to P1. Actually, good pointer and bad pointer. So it loads the sectors one at a time, looks for a signature, and if it finds it, it sets the jump offset. Right. Search for boot sector. And this is good signature. And is it returning anything useful? Yes, it's setting the carry flag. So we can change this to a bool. Place that in a register. CF. There you go. If the signature matches, then this comparison here will clear C so that when we actually do the return, carry is clear. If we run out of sectors, it returns with carry true, indicating that it's failed. Excellent. Right, now this is called from long distance calls. We know that this therefore must be load and run boot sector. So yes, we search for the boot sector. If it succeeds, let's rename this to failed. Then we do a thing. Then we set up the jump instruction and we jump. Let's change this to a byte. Right, this explains why I couldn't find anything that sets the segment, because the segment is always 0, and I believe that the memory gets initialized on startup. So it's loading the sector into our buffer in low memory and then jumping to it. Now, why they didn't just do a jump F to address of the buffer, I don't know. What does this do? Oh, this is big. This is loading the rest of the program. Look, we've got our 9 again. We've got calls to executive entry point 2. And let's just do a thing. I'm going to create a enum, which is going to be enum executive operation, and add a value, which is executive operation load sector. That was 7. And we're going to add a value xop change track. I think it was, to 2. Okay, so now I can change the type of this function, so this is no longer a byte, it's a enum executive operation. So here you can see that we're now actually doing executive entry point, xop load sector, and xop change track. I think these are all referencing magic global variables, so the argument is unused. So here there is a counter coming in dx. And when the counter reaches 0, it stops. So that must be the number of sectors. So let's add that as word sector count and put that into dx. And let's call this load program. Now it's using the the current sector, current side stuff that we set up when we search for the boot sector. So I don't think we actually need to understand this. So load and run program. This is not setting the argument to load program, which means that search for boot sector here must be returning it in DX. Yeah, here we go. It's actually returning several things, DX and AX. So this is a problem with decompiling to C, in that C only allows a single return value, while, of course, machine code, you can do anything. It doesn't have to make sense. So yes, this is clearly loading stuff out of that boot sector. Yeah, BX is the pointer to the buffer relative to segment 0. We now know the layout of the buffer. So I think that the only thing we need to actually make a floppy disk that boots is to figure out what this is pointing at. It'd also be nice to know where this is called from. 15D. Is it? It can't be FF, right? No, we tried that. And it's not F8. But I haven't seen any other segment addresses in use. Judging by where this code is, I would expect it to be in FF. Maybe this isn't a function. Maybe this is a data table. Because if the boot sector signature contains disassemblable machine code, that will get things confused. 15D. No, I don't think that's right. I think this is part of an actual function. Incidentally, I suspect that this port manipulation is turning the floppy drive motor on and off. Now, if I was a signature table, I would be next to the function. So if we've got load program, then we've got a mysterious thing. Goes down to here. This is interesting. This is calculating the sector side and track of a particular sector in absolute numbering. So this is absolute sector. This is calculate CHS. And this is called from load program. Yeah. And this is using that AX value that got passed into this from search for the boot sector. So this is going to be absolute sector. And this is in AX. And, right. Okay. I'm making R noises because I saw this earlier and didn't know what it was. I couldn't find anything that referenced it. But now I know what it is. This is the boot sector signature. Boot sector signature. F000 F95D. So it's actually relative to FF80. Let's just test that. FF80. There we go. So we know that for this to work, then CS must be FF80. Right, this means that this is actually at address 0 relative to its segment. This is a bolt-on chunk of code they got from somewhere else that just got dumped into the ROM somewhere. So there's nothing else here. It's padded with FFs above and below. All right. One more thing I want to do is bytes left to compare is OB. This means that we know that our boot sector signature is not 32 long, it's OB long. So it's this. Oh, I know what it's doing. Oh, that's both incredibly clever and incredibly ugly. You can make an MS-DOS format disk with one file on it that starts with that signature, and this will completely ignore the file system and brute force search until it finds a file starting with that signature in the first 10 sectors of the disk, assuming there's no other verification done. Provided the file is contiguous, that is not fragmented, then the rest of the code will load it fine. That's fascinating and horrible. It means they didn't have to put a full file system in it. I bet that the word processor software that loads off disk does have a file system in it, but they just didn't bother putting one in ROM. Well, that's a thing. Okay, let's try and clean up the board a bit. Yeah, this vacuum pump solder sucker is working extremely badly. It seems to have left a mark on the PCB, which I don't really like. Well, that took forever and a lot of solder braid, but I did eventually manage to get one of the chip's footprint cleaned up. So now I can actually put a socket in. After I clean the enormous amount of flux off the board and my workbench, however. This is a miserable process. That took me about an hour, just one of these. There is something I'm just not doing right, and I cannot figure out what it is. Well, that was a deeply miserable experience. It took several hours and a small pile of copper desoldering braid, but I did manage to get sockets installed. So, assuming the PCB survived all my wrenching around, there's now a plausible chance that this thing still works. Getting the holes cleared was way harder than it should have been. The solder braid worked on most of them, and some of them I just couldn't get the solder out at all, and my soldering iron had a lot of difficulty heating them. Now, I did find some of the legs on the chip seems to be longer than others, which makes me wonder whether my ineptitude caused little fragments of leg to get stuck in the holes, and maybe that was why there was a problem. But anyway, it seems to be done now, and the legs are still long enough to go into the sockets. So we place this here. Let's just do a little bit of leg bending. So we place this here and push. And done. All right. Let's take a look at the other board. Now, this is the 8051 based board. This is much simpler than the other one. It's using 7.4ls logic rather than gate arrays, which means it is possible that I might be able to understand it. And, glory of glories, the chip is socketed. So let's take this out, and I'll read it and see what we get. Says it's a 537E10280. Okay, over to the computer and the chip reader. Scraping the label off the chip reveals it's an MBM2764. So we read it. We got something. What do we have? Well, that looks like stuff. That looks like a table of some description. I wouldn't expect to see many strings. And that's it. There's not a lot there. Okay. Let's load it into Xero and see what there is. The 8051 is a deeply weird 8-bit CPU. It's got a strange architecture that's quite hard for tools like Xero to decompile, but it will at least work as a disassembler. The reset vector is at 0. That jumps to here. Does some startup stuff. So what we would expect to see here is initializing of various ports, which is clearly what it's doing. Sets the stack, sets some stuff. This is calculating a checksum, I think. This all looks very checksummy. So if the checksum matches, then it does this, which is clearly the main code of the thing. Otherwise, it jumps here and spins. In other words, if the ROM is corrupted, then it will refuse to start up. This is definitely worth doing, given that this thing is controlling 3, possibly 4 chunky stepper motors. Then you want to make sure the code is intact. This calls a thing. It then waits for a particular bit to be cleared. 2e.3 here means bit 3 of the variable at 2e, and then it jumps to this code. As the 8251 doesn't have threads, this will be being set by an interrupt somewhere. So I think this is doing initialization or startup. This could be the code that resets the print head and print wheel, and then it is waiting for the operation to finish, and then we go on to the main loop of the program, which is empty. Interesting. I do notice that this infinite loop here doesn't appear over here. So this is Xero getting confused about the fact that this code is clearing a bit and then looping, waiting for the bit to be set. And Xero is assuming that because nothing has changed the bit since it's been cleared, it can only ever be true. I can actually turn that off and suddenly more code shows up. So yeah, it is actually calling OC47, which I suspect, yeah, this looks like the main loop. So I can actually fix this in a rather better way by opening up the memory map and setting the memory as volatile. Let's just set it all as volatile. That prevents it from remembering the old value of a register. It does slightly cripple its ability to produce good code, but for this system that is worthwhile. There we go. And our loop is now much more sensible. So over here at C47, what I'm expecting this to be doing is reading characters from the communications channel from the main board, which is probably just a serial stream, and then doing stuff with them. I don't see any obvious references to the serial port. Now I've got the datasheet for the 8051 over here, and it refers to the special register SCON used to set up the UART. So here it is, and it is being initialized in 3 places. I can see it being initialized to BO, which is 1011, 90, which is 1001, and 0. So REN is the reception enable bit. It is being set, that is turning the UART on. This is 10 in both places, mode 2 for the UART, which is a 9-bit UART. So yeah, that should totally be working. One problem with the 8251 is that every opcode has a meaning. So disassembling random garbage produces what looks like code. I think what I've done here is I'm disassembling a data table because this code doesn't really make a lot of sense. Like, why is there a NOP there? Why is there a jump there with some code immediately after it that doesn't seem to be referenced? All these byte values are suspiciously small. So I think I've actually done this wrong. And I need to clear all this, at least until we get to sensible looking code. But this, I think, is real code. It looks plausible, and I can see here that it's actually being called from a bunch of different places. So I think this is valid. Here it is loading 997 into a data register. It then loads a byte and jumps through it. That's a little bit odd. Here we go. I was misled by the @ sign. That normally means that an address is loaded from the following expression. But in fact, it means that it's jumping directly to that address. So this is one of the entry points. And the next one is at 7 plus 615, which is here. And yeah, it's pretty obvious where they're going to be immediately after a jump instruction. Looking at the top of the ROM, I can see this interrupt servicing routine. This is called whenever a receive is complete or a transmit is complete. So we should be able to follow the code and see it reading or writing characters. In fact, here I can see it reading the TI bit. Has a character just been transmitted? If so, it does this. So this branch means that transmission is complete. This function is only executed when a send or a receive is completed. So if it's not a transmit, it must be a receive. So this is the code path for doing a receive. Let's see if I can clean this up slightly. I prefer it to inline this, but anyway, this is the receive path. So, no, I'm sorry. This is the receive path because here you can see it's clearing the receive bit. This port here, sbuff, is the serial buffer register for UART. So I believe this to be the byte just read. Rename that to value. RB8 here is the special 9th bit of each byte. So if it's 0, we go down this path. If it's 1, we go down this path. I believe that it's actually using this extra bit to distinguish between commands and data. And I think that this is the command path and this is the data path. Here is an interesting 8051 feature. Here it is writing the value into a memory location whose address is in R0. R0 is not set in this routine. R0 is a global register allocation. The 8051 has quite a lot of registers, and one common trick is to assign some of them to global values. And in this one, it's clearly the buffer pointer for the input buffer. So ideally, if we find other places where R0 is used, I should be able to figure out where the buffer is. Okay, this is interesting. Down here in this piece of code, you can see that the highlighted lines don't match all the lines of machine code. Xero has been unable to decompile this where it's setting R0. Now this is the code path that you get when you're doing a receive, but the magic 9th bit is set. I think that when the magic 9th bit is set, it's starting a command. That then resets R0, which is a pointer into the command buffer. And then the rest of the code up here fills that command buffer up. I think this is where the command parameters go. You see it is read from a lot of places and written to not many. So I think that the system board will start a command with the magic 9th bit set. Then there will be some bytes of parameter. So I don't expect this serial link to actually be sending ASCII. Here it is decrementing 3D. If 3D is 0, we set this bit. That bit is tested here. So you only do this if that bit is clear. But that could well be counting down the remaining characters in the command. So where is it written from? It's only ever written from our handler. It is actually set down here. From the code path you get if 23.0 is true. And that is set down here when we get the first byte of the command. So I think the command format is you get a byte with the magic 9th bit set, which starts a command. The second byte goes through here and contains the length of the packet, and subsequent bytes go through here, which actually fill the buffer. So we can actually assign some meanings to these. So this is RI waiting for length bit, and 21.2 is RI received command bit. A byte comes in with the magic 9th bit set. If we have received the command bit, proceed with the rest of the command. Otherwise, go down here. So that can be current command high, current command low. This has just added the length of the command on to current command low. So the low nibble clearly has something to do with the length. And we see that 3D here is the length. So this is going to be RI current command pending bytes. So here you can see this is being decremented. Sadly, I haven't found a way in Xero of making individual variables volatile or not. So we're stuck with this rather than just current command pending bytes equals current command pending bytes -1. So this looks like 23.1 is current command complete. So if we go down to current command complete, we see that it is only being read from the command handler. So this is not the flag which triggers the actual execution of a command. Unless, of course, Xero has failed to decompile this properly. It doesn't really work very well on the 8051. This is the code path where the current command is complete, but we get another data byte. And it looks like what it does is abandon the current command. It does seem to be adjusting current command low as each value comes in. So that is also not being read from outside the handler. Somewhere there must be some code that actually handles a command from the interrupt buffer. Over here in the main program, we have this loop, which looks very suspicious. 2e.3 is one of the variables we saw being manipulated in the interrupt handler. And we see here, it gets reset and then it does some stuff. And in particular, it's reading from 3.1, which is one of the bytes from the command buffer. And here again, this is the first byte of the command buffer. So it's plausible this routine might handle the command. And this is big and has a huge switch statement in it. Yes, this is our command handler. And yes, it is reading out of the buffer. So we know that this is actually the current command. And Xero is doing a terrible job of decompiling this switch statement, but it hasn't even disassembled some of it. This is one of those jump tables. So that here we have offsets relative to the beginning of the jump table. And I think this may just be garbage. So the first one is at OXD3B plus OX2B here. Does this disassemble? Yes, it does. So yeah, I think these are the command handlers and each one does a particular thing. So after some cleaning up and poking around, I discovered a rather interesting thing, which is that the first thing our handle command function does is work through a loop where we have, it's down here, a list of particular commands. And these are clearly special and require special handling. If the command is found, it does this thing. And you notice that it is doing something with R0. So possibly these commands take more parameters later? Not sure. But the command table is now pretty clear. The commands go up to 1C. However, Xero doesn't know this and I haven't found a way to tell it. So it's gone mad and tried to assume that every possible byte value is a command, which has actually caused a whole bunch of problems. I don't know how to persuade it not to do this. But we can see that the valid commands look reasonably simple. And that the last command, which is 1C, here we go, that just resets the board, which is what we would expect to see as one of the commands. So I think I have enough here that if I were willing, I could figure out how to talk to the board and how to send commands to it. And from there and a bit of experimentation to see what the commands did, I think I could probably figure out what all the various ports were hooked up to, but I'm not going to do that now. So that's it for now for the printer board ROM. It does occur to me that given that this board is designed to drive a number of heavy-duty stepper motors, at least 3, possibly 4, that is left to right, up and down, daisy wheel round, and potentially advancing the ink ribbon, and also to drive the solenoid, this could very plausibly be repurposed as a 3D printer control board, or some other system that wants to drive stepper motors. I could definitely see this as the control board for something like a robot. I will have to think about that. Next up, let's take a look at the print mechanism. which is kind of big and doesn't really fit on my workbench, but it's pretty straightforward. It's your standard XY setup. This black roller holds the paper. It's driven by this stepper motor and the gearbox here. There are some knobs to let you manually turn it. The print head itself moves back and forwards along this rail, and that is driven by a stepper motor at this end, which is direct coupled to the belt here. So you should be able to see that rotating. Here we have the brake. This controls how tightly the paper is held to the roller. So when it's in one position, I forget which is which, the paper can be manually adjusted freely around the platen. And when you're happy with where it's put, you flip the lever and now it's gripped tightly and will only move when the platen rotates. The other is this thing. This holds the output end of the paper against the platen and just keeps things tidy and prevents the paper from getting stuck underneath the lid. There's also a micro switch under here so that you can stick a piece of paper in, pull this, wind it round the print head, then you give this another push and it triggers the micro switch, and that tells the typewriter that you've loaded a new piece of paper and it will automatically wind it to the right place. Bit of a knack to making these work, but they do work pretty well. So now we come to the print head, which, if I turn this over, contains a lot of complexity. Let me figure out how to remove this from the rest of the mechanism. So here is the print head itself. It's a large, heavy chunk of machinery. Getting it off was harder than it should have been. The belt that moves it along the rail is quite firmly attached here, so I ended up having to take the rail off. There is probably a trick that allows you to uncouple the print head from the belt for doing maintenance, but I don't know what it is. On this side, there's the ribbon cable, 2 ribbon cables actually, that connect it to the rest of the machine. And for some reason, a piece of thin copper. Don't know what this is for. Might be just a grounding strap. It's not stiff enough to be a spring. Zooming in here, you can see the mechanism. This is the daisy wheel itself. Each of these arms has a letter embossed on it. And here is the hammer. It rotates the daisy wheel into position, and then the solenoid in the hammer fires, and it mashes the daisy wheel against the paper through the ink ribbon. The ink ribbon is this black plastic thing here. Removing the daisy wheel is easy. You do this, and you do this. Installing a new daisy wheel is easy. You do this, and you do this. There is a sensor to allow the machine to know where the top of the daisy wheel is. So whenever you change daisy wheels, it will rotate until this mark here, which you can just make out on the camera, is at the top. I don't believe it uses that mark to sense it. I think there's another optical sensor elsewhere, but that is the index stop for the daisy wheel. Once the machine knows that this is at the top, it then knows how far to rotate the daisy wheel to get any given letter. The ink itself is held in this cartridge. It's a long strip of plastic tape coated with probably carbon black or something similar. Unlike a traditional typewriter printer ribbon, this is strictly single use. When the hammer fires, it transfers all the ink from the ribbon onto the paper and in fact leaves little clear marks on the ribbon where you can read all the text that's ever been printed with this ribbon. Unfortunately, you can't see them on this one because I've wound it on too far and there's a ratchet, so you can't pull it back again. Oh well. So these things contain, PII, like actual sensitive information. I did get one of these once where the ribbon was full of, insurance numbers and phone numbers and names and addresses and all stuff like that. So they shouldn't really have given me this. Oh well. With the cartridge removed, you can see the head more clearly. If I rotate the wheel so a letter is under the head and then move the hammer, you can see it pushing the individual letter forwards. The daisy wheel is, I think it's plastic. Yes, it's plastic, which does make me wonder how long it lasts. Oops, that's not in place. There we go. There we go. Underneath the hammer, you can see the stepper motor that makes the daisy wheel go round, which is reasonably sized. On the underside, there's a little DC motor, not a stepper motor. This turns a whole bunch of gears. You can see this mechanism in here. This does a bunch of different things, one of which is to rotate this, which in turn rotates this, which pushes up into the ink cartridge and actually does the business of winding the ink forwards. It also, and let me just reinstall the cartridge for this, to tighten that again, like so. If I hold it so that you can see the wheel and the ink ribbon, as I rotate this, it moves the whole ribbon up and down. This allows the typewriter to use both the top and the bottom half of the ink ribbon. So it uses rather wide ribbons but gets through them at half the speed, which is kind of cool. You may have noticed this thing. This is a second printer ribbon. This contains a transparent, slightly sticky ribbon, which is used for removing letters from the paper. And in fact, you can see there the marks of the letters which it has removed. This also contains a record of every letter deleted, which should be considered PII as well. But because you tend not to delete every number in a phone number, you're unlikely to get anything useful for this. Over on the side here is the cam, where if I rotate the motor, you can see it moving. Try and avoid putting my fingers on the mechanism. You can see it moving the print ribbon up and down. There's also a second solenoid here, or possibly a relay. It moves a little metal hook in there, but not very far. I think this has got to do with triggering the delete mechanism. If this goes down, there's a little thing underneath here which looks like it would hook onto it, but doesn't actually move quite far enough. So I'm not sure about that. It's all quite subtle. Another interesting feature is that down here inside is a encoder wheel with a whole bunch of marks on it and holes and things. And I believe this allows the machine to know what position that DC motor has moved the mechanism. Again, it's probably got to do with working the erase ribbon. I suspect it has to rotate to a particular position, then it fires the solenoid, then it rotates more, and that engages a thing which does more things, etc., etc. They have gone to the trouble of connecting all the mechanism of this thing to the little PCB with these plugs, which is nice. And under each plug, there is one of these plastic things. What these are for is that you can push them and unplug the plugs, and you can pull them and plug them back in again, which is very cool. Nice piece of design for maintenance there. Back on the dining room table, let's take a look at the power supply. It is old-fashioned and very simple. There's a gigantic transformer that turns mains voltage into low voltage AC. Then there is a gigantic rectifier that turns that into DC, and a gigantic capacitor that turns that into more or less smooth DC. This thing down here then does DC to DC conversion to generate all the various voltages the thing requires. In the back here, you can see that there are some large power transistor type things which are bonded to this aluminium back panel that is in turn screwed to this enormous chunk of aluminium here, which will be a heatsink. But I want to look at this thing on the workbench, so let's see if I can remove it. That was easier than I expected. There were only 2 screws. And here it is. It's commendably well labelled. All these pinouts have labels. This is for the printer control board. This is for the application board. This connects to the monitor. This I'll get onto in a moment. You can see that it uses 12 volts, 5 volts, 32 volts here, which is probably to run the big stepper motors, and 16 volts here for running the monitor. The monitor doesn't have its own power cable, it's powered from this board. The DC comes in here, runs through this huge chunky capacitor, does stuff, and then is emitted. Now a bit of probing reveals that this black wire, let's do it this way around actually, is ground, which means that the white wire must be voltage. And in fact, if I check the 32 volt line, clearly the 32 volt line is just producing the raw unregulated power from the transformer. An interesting thing is if I actually try this the other way round, so it beeps for a bit and then stops. That is this capacitor charging up. So you have to be careful with that when measuring continuity. Now it's charged, it's no longer producing a current flow, it's therefore no beep, but it still works on ground. Looking at these 2 connectors, they have a few signals in common, apart from power and ground, obviously. AirStat is, I think, serial connection between the 2 boards, how they talk to each other. Although there does seem to be 1 rather than 2, so I wonder if it's one direction. Whether the application board communicates with the printer board, but not the other way around. But I'm sure I saw in the printer board code that it was writing to the UART, so not sure what's going on there. PNorm and NPOR are probably to do with power control. They might tell the various boards when the power is good, that is all the capacitors charged up and the voltages have stabilized. Looking at the video connector here, we can see that the H-Sync and the V-Sync are routed straight from the applications board, but the video signal is not. In fact, the video signal is produced by this chip here, which processes the signal from the applications board. This is an inverter. It might just be being used as a buffer, but then the application board would have to generate the inverted signal, so don't know what's going on there. But now let's come to this thing. Looking at the underside of the connector allows us to very easily figure out what's connected to what. There are a couple of pins here which are connected to ground. This one is connected up here to the applications board. This is the NPOR line. This one is connected via this much thinner track to this, which is the SDAT line. And these 2 are connected to this, where there is in fact no pin on the other side. This is the key. It's the missing pin that matches a filled hole in the connector to ensure you only put the connector in the right way around. That connects up to here, which is the other side of that big copper choke, which is in turn connected to this, which is the 32 volt line. So this is providing 32 volts of power down to this connector here. And we seem to have a power regulation signal and the SDAT line. So despite the fact that this thing has the same socket as the monitor, I think this is an accessory connector. It's probably a computer interface to allow you to use the typewriter as a printer. The 32 volt line is intended to power whatever the interface is, and NPOR, if I'm right that it's a power signal, is used to tell the interface that the power is good. Remember that because this huge capacitor is in play, the 32 volt line will actually stabilize quite slowly, as the voltage will rise as this thing charges up. So what does that NPOR thing actually do? Well, we can trace it from here to here to here. This is the NPOR line on the applications board. The track is slowly getting wider as we go. To here, that's on the auxiliary connector. But then it goes up here to this. This is a capacitor, the other end is here. And to this chip, where it terminates. And that is a transistor. So I think that what's going on there is that once the voltage reaches a certain level, this thing switches on, and this NPOR line then gets grounded or brought high, and that signals to the rest of the system that it's good. You can see that the transistor has one leg on ground. The middle leg then goes up into this mass of components and eventually ends up in this inverter, which has probably got something to do with it. So there's only one thing to do now, and that is to try powering it up and seeing what happens. I've pushed some screws into these spade connectors just to give the crocodile clip something to clip onto. Make sure these are well away from each other. So now I should just be able to dial 32 volts into my bench power supply and see what happens. However, I gather that these power supplies do not get on well if there's no load. So, a little hesitant to do this. Let's plug the printer control board in, which will at least provide some 5 volt load. I found this very handy wedge-shaped USB hub. Okay, so my bench power supply only goes up to 31 volts. Nice. Let's go to 2 amps. On. Okay, that has settled down at 300 milliamps at 31 volts. That's 10 watts. That's quite a lot. Let's check a few voltage rails. So ground there, 12 volts here. Make sure that's visible. 12 volts. That's working. 5 volts. That's working. 16 volts. That is also working. So I think that's functioning. So let's turn it off. Let's try something a bit more exciting. These are the stepper motors I took off the printer mechanism. Let's plug them in. This one, this was for the print head motion. That goes here. This one is for the paper feed, and this goes here. Although I noticed that this connector has 5 pins and this has 4, so make sure to put that in the right place. Admittedly, that is subpar by Xerox standards from what I've seen so far. They usually do better than that. And this is for this little micro switch, so put that on here. Now, I don't necessarily expect this to do anything when I turn it on. I don't know whether the printer control board will try to reset the print mechanism until it's commanded to do so by the applications board. But let's give it a try and see what happens. Okay, power. No motion, though I do notice it's now using an extra 5 watts. And yeah. This one will turn. That's locked. So this is powered but stationary. If I turn it off again, I can now rotate it. When it's powered on, it's solid. Okay, the printer board is working. Let's move on. Here's the print head. Let's plug this in. The connector for the print head is under here. It's this thing here. In a very strange and rather subpar piece of Xerox technology, they didn't key it. So I had to check my footage to figure out which way to plug that in. But that goes on here. Okay, let's power on. My thought is that it might refuse to do anything unless the sensors in this thing are reporting valid results. Well, that did a thing. It's clearly still refusing to start up, but it did move this slightly. And the green LED here has lit up. So that is functioning. A thought has struck. When I showed off the print head, I carefully rotated the daisy wheel so the index mark was at the top. So in fact, it doesn't need to do anything to get the print wheel aligned. So let's try rotating it a bit and then power it on and see what happens. And go. Well, it moved it a bit. Try that again. If I turn it like halfway round, what does it do? And go. Yes, okay, it is clearly homing the daisy wheel, but it's not homing the print head. All right. Next step. Here is the applications board, and here is the crinkly ribbon cable that hooks them together. So let's plug these up. This goes on here. And this goes on here. The shielding they've put around the ribbon cable makes it very stiff. This is the moment when I find out just how badly I broke the applications board. So let's turn it on and see what happens. And go. It works. I mean, the keyboard's not plugged in, but it spun this motor. Oh, it's now turned off. It's free. So it was clearly trying to home the print head. Now there's an interesting thing. I haven't found a sensor to let it know when the print head is at the end of the... There will now be a short pause to let my heart rate drop again. Yeah, that was gonna happen. Thank goodness for the overcurrent trip. I wonder if this thing still works. It should do. The only thing that this will have noticed is the power suddenly dropping out. What I was about to say before I was so rudely interrupted is that maybe there's a sensor here. Possibly it's this thing. I can't tell what it's connected to inside, if anything, but that is a reasonable supposition. Okay, let's power it back on again and see if it all still works. Let's not have that copper bit touching the applications board. Are we clear? Yeah, let's go. Yeah, everything is still fine. And it even made the beep to let me know it's turned on. Now, if I try pressing this micro switch, that should make it think that I've pulled the lever back and it wants to feed a new piece of paper. Very nice. So what it's doing over here is moving the print head into the middle of the platen, and then it winds this the right amount to get the paper in the right place, and then it puts the head back to where it was. Okay, behold the power of my fully functioning typewriter, although I haven't plugged the keyboard in. It's too big to fit, and it's mostly broken anyway. Yeah, the daisy wheel is now locked by the stepper motor. Although it's not that powerful, I think I can push it past, but I won't. This is not locked, I think that's stiffer, but it's not locked. Let's try turning it off. Yeah. This is attached to the paper feed, and you are supposed to be able to wind the paper by hand. So it makes sense that this doesn't lock hard enough to prevent you from doing that. They're stepper motors. You energize the coils and it then holds the head in position. The head only moves when you energize the coils in sequence to pull the head around. So yes, a stepper motor can lock its head in place. So no motion, but it's still consuming power. And I should add, that peaked at 35 watts and is idling at 24 watts. So this is not a cheap thing. I wonder if these resistors are getting... Ouch. Yes, I know where a lot of that power's going. These things are hot. So I've done some rearranging to make the oscilloscope visible, because there's one more thing I want to try. I've connected some jumper cables to the video output. So let's power on. And I put white stripes on the motors here so you can actually see them go round. Like so. We wait for the beep. There we go. So let's try the white wire. This is the vertical sync feed for the monitor, and this is showing 77 Hz refresh rate, which is quite high for a black and white TTL monitor. Okay, let's try the grey wire, which is the H sync. This begins each scan line, 18.2 kilohertz. And finally, let's try the purple wire, which is the data. And currently the monitor is just showing that 1 down in the bottom right hand corner, so not much is there. But we can see that there is something there, and it seems to be active low, so that when the signal is high, then it's displaying black. And I can see here, these are probably the multiple... Let me adjust this. So we have, it looks like 6 scan lines. So these are each scan line. So yes, that is displaying 6 scan lines for that one, which is interesting. I assumed there would be 8, to be honest. Okay. Well, that's very interesting and not at all what I expected. And that brings me to the monitor. Here is the monitor. Now you've seen the monitor. No, I'm not going to open it up. Even small black and white monitors like this one can get cranky and hurt you if you touch them inappropriately, so I'm just not going to. There isn't really anything inside I'm interested in anyway. I'd much prefer to keep this as a working monitor. Interesting features on the outside include the swivel arm and the brightness control. There are no other controls. I know from earlier testing that this thing is perfectly in focus and produces an amazingly clear, crisp result. So I don't need to adjust anything. I'm just going to leave this untouched as is. So that's basically it. It's pared down to the bottommost layer. The only thing left is this sheet of galvanized steel, which provides grounding. Here there's an interesting rubber mount with this braided grounding strap over it. The print mechanism itself sits on top of this, and this provides vibration isolation from the table and makes it much quieter when printing. Daisy wheel printers are notoriously loud. And there's also another thing which took me ages to pick up on. The system board here normally goes about there with this connector plugged in here, and that makes the hatches give access to these 2 connectors here, of which one is populated and the other isn't. These are clearly for extension peripherals. For example, a spell checker extension. I don't think this has its own built-in spell checker, but if these give access to the system bus, you could certainly add one. Just to give you an idea of how much there is, here are all the pieces exploded over my dining room table. I suppose I really ought to try and put it back together and see if it still works. Oh good, it still works. So I was going to leave it there. This video is far too long as it is, but there is something I have to try. This is a very minimal boot sector and program based on what I found out from reverse engineering the ROM. This gets written to a floppy disk. The first thing we do is skip 2 sectors because the boot sector search routine starts at the 3rd sector. That is sector number 3, sector index 2, because sector numbers are 1 based. The boot sector itself is down here starting at line 6. It starts with the signature, which we found from the ROM. Then there's a gap. Then we have to tell it where the main program body starts. We're not using that, but we have to have at least 1 sector of program. Otherwise, bad things happen. It decrements the sector count after it's loaded a sector. Then we have the start address, which is pointing to the next bit of code below, and the number of sectors in the program. The program itself turns interrupts off. It then pokes a port, which I think turns the floppy disk drive motor off, and then it spins. So what I'm hoping is that when I write this and boot it on the machine, I will see the floppy disk drive motor stop, and then it will just hang and do nothing. That will mean that I've actually managed to execute code on it. Okay, so assemble with NASM, and now we put the assembled program onto the floppy disk, which is done. So now all there is to do is to go over to the machine and see what happens. Okay, moment of truth time. I've set the camera up so you can see the screen, not that anything will appear there, except possibly an error message if it doesn't work. And I am doing this for real the first time, so let's see what happens. Damn it, that didn't work. Well, I made it work, but I do now feel quite silly. Here is the boot sector that I ran, and you may notice that it looks completely different from the one I just showed you. There's 2 reasons for this. The first is that if you go back to Ghidra, here is where it's starting the search for a boot sector, and it's starting on side 1 of the disk, not side 0 of the disk. So my idea of where the boot sector should go was in fact completely wrong. The other is a little bit more serious, and is that I figured out why I couldn't find any references to load and run program here. And the reason for this is that there aren't any references to load and run program. This piece of code is totally unused. I realized this when I found this, which is another boot sector loader. It's a completely different one in a completely different part of the code, which searches in a completely different place and looks for a completely different boot signature. In fact, the signature for this one is much simpler than the other one, resulting in a boot sector that just consists of this header at the top of the sector, and then you get the entire rest of the sector for code. This field is used for something that I haven't figured out. It seems to have to do with loading code, but it only ever seems to load 3 bytes, so that requires further investigation. But I do now have it working. So let's go back to the computer and I'll show you. Well, here we go, and you'll be relieved to see that I've remembered to turn the brightness on the screen up a bit. So that it should now be visible. And yes, I may have extended the program a little. I found a function which draws the status line there, so I'm just calling that. I still don't know where the screen is in memory or anything. So, that seems like a good place to leave things. Reverse engineering the rest of this shouldn't be that bad. Now that I can actually run code, I can figure things out experimentally rather than relying on pure analysis of the ROM. That said, it appears that the gate arrays are doing a lot of heavy lifting, and figuring those out will not be straightforward. So I'm still deciding whether I actually want to do any of that. It'd be quite a lot of work, and to be honest, the computer in this thing is not very exciting. It's just another 8086 single board computer. I already have one of those from a IBM word processor, but I think this one may actually have more RAM, so we'll see. The other thing is finding something to run on it. MS-DOS would be possible. It would be difficult to port because this isn't a PC, and because it's not a PC, it won't run most MS-DOS software, which assumes that it's running on a PC and will try to talk directly to PC hardware. CP/M86 might be an option. It's much easier to port, and 256K is reasonable for CP/M86, but I've never worked with it, so we'll see. Although, that does sound like a challenge. But if I do this, it's unlikely to be with this beast here in one piece. I'm afraid that this thing is just too big to keep. It's so big I'm having trouble getting it all on camera. So most of this is probably destined for e-waste. If anybody wants it and can come to Zurich and collect it, because I'm certainly not going to post it, they're welcome to have it for free. But if not, I'm probably going to strip off the bits I want, like the monitor, the keyboard, floppy disk drive, system boards, all the many stepper motors, and the rest of it is probably just going away. These things are just too damned big. Any takers, please let me know as soon as possible. So I'm going to end it here. This has been a long and very detailed teardown. I hope you all find the details as fascinating as I do, but then if you're still here, that's probably true. All the various files and things are uploaded to Internet Archive. See the description for the links. And with that, the only thing left is to say, I hope you all enjoyed this video. Please let me know what you think in the comments, and I will see you all next time.